Welcome to section 5.1, Systems of Linear Equations in Two Variables. Objective number 1, determine whether an ordered pair is a solution of a linear system. So a system of equations is two or more equations with the same variables. The solution to a system of equations with two variables is the ordered pair that satisfies both equations. So in this visual representation for symptoms of physical illness among college students, we have two equations that are represented by two lines, one in red and one in blue. We have graphed those two equations, and their intersection point would be the ordered pair that satisfies both equations. In other words, that ordered pair is what makes the equations true. There are three types of solutions for a system of linear equations. The first one is one solution. So similar to the example above, the intersection of two lines would be our solution. You could have no solution, and this is where your equations are parallel to each other, or infinitely many solutions, where your equations are the same line. So in one solution, a system of linear equations that represents intersecting lines would have one solution. No solution is where if a system of linear equation represents parallel lines, then the lines do not intersect and the system has no solution. In such a case, we call this system inconsistent, and we'll be looking at that more in an upcoming section. Infinite solutions, this is if a system of linear equations represents the same line. Then all points on the common line satisfy each equation. Therefore, the system has infinitely many solutions. In such a case, we would say that the equations are dependent. Note that the solution of a system of linear equations can sometimes be found by graphing both of the equations on the same coordinate system. So for a system with one solution, the coordinates of the point of intersection would give you the answer to the system's solution. So note, you can always check whether your ordered pair is a solution to the system by graphing the equations. So now let's determine if the ordered pair is a solution to the following systems. So we are given two systems here, each with a potential solution. We need to check if they are solutions. Now we're going to do this algebraically, and then I encourage you to check it graphically. Okay, so let's do the first one. So in order to determine whether this ordered pair is a solution, we're going to have to substitute this ordered pair into both equations. So we'll take 2, and then the x is -3 plus 6 times 5 equals 24. And that would get us -6 plus 30 equals 24. -6 plus 30 is 24. So that's true. So it's a solution to the first equation. Now let's check the second. We have -3 plus 5 times 5 equals 3. So that's -3 plus 25 equals 3. So that would be 22 equals 3, which is not true. Okay, so although the ordered pair satisfies the first equation, it does not satisfy the second. Therefore, -3, 5 is not a solution. Okay, let's do number 2. So we'll substitute in 0, 1/2 into both equations to determine whether it's a solution to the system. So 5 times 0 plus 10 times 1/2 equals 5. So that's 0 plus 5 equals 5. So 5 equals 5. That's true. So 22 times 0 minus 6 times 1/2 equals -3. So 0 minus 3 equals -3. So -3 equals -3, and that's true. Therefore, the ordered pair 0, 1/2 is a solution. Awesome. Objective 2, solve linear systems by substitution. So finding the solution to a linear system by graphing equations may not be easy to do if the point's coordinates are in fraction form. For example, a solution of -2/3, 157/29 would be difficult to see as an intersection point on a graph. The substitution method involves converting the system to one equation in one variable by an appropriate substitution. So this is our first method to solving a system of linear equations. So to solve a system of equations by substitution, your first step is to solve either equation for one of the variables. Step 2, you're going to substitute this expression into your other equation so the equation is in terms of just the variable. Step 3, you will solve for the variable. And then step 4, you will use substitution to solve for the other variable. And of course, you can verify that that ordered pair is a solution by substituting it back into both equations, making sure it makes the statement true. So let's solve the system of linear equations, and we're going to start with number 3. All right, so I have two equations here, and my first step is going to be to solve either equation for one of the variables. Now you can choose either variable, x or y. I am going to choose y. Now I need to identify which y variable I want to isolate, either from the first equation or from the second equation. I'm going to choose the second equation because the only coefficient the y has is -1. So I'll be able to isolate y all by itself. Okay? So when I do that, my system is now 2x plus 3y equals 10. I'll have 5x plus 26 equals y. Okay? So that's me getting y by itself. So I'll show you the middle part here. So to get y by itself, I'm just going to switch the y and 26. So I'll add it to both sides. Okay, so that was the middle step. All right, so now that I have my system, I now can substitute in the expression that I have equal to y into my first equation. So I'll have 2x plus 3 times 5x plus 26, because that's y, equals 10. Okay, so this right here is y. And now I have an equation all in terms of one variable, x. Okay, so I'm going to now simplify. So I'll have 2x plus 15x plus 78 equals 10. Combine like terms, 17x plus 78 equals 10. Move the 78 to the other side. That gets me -68. Divide by 17, and I get x equals -4. Okay. So now that I have x, I need to find y. But I have an equation for y. Y equals 5x plus 26. So if I substitute in x, which is -4, I'll get -20 plus 26. So then y equals 6. So my solution will be the ordered pair -4, 6. right, let's do another one. Number 4. Okay. So in this system, my second equation already has a variable isolated. So I don't have to do any extra work in terms of isolating either variable. So I can just move straight into step number 2, where I substitute in my expression for y into my first equation. So I'll have 2x plus 4 times 5x minus 7 over 4 equals 4. Remember, this is y. So I'll distribute the 4. I'll get 20x minus 7 equals 4. Combine like terms. Move the 7 to the other side. That gets me 11. X equals 11 over 22. So then x equals 1/2. Now that I know what x is, I can substitute it into the equation for y in order to determine the value for y. So y equals 5x minus 7 over 4. I'll substitute in 1/2. And then I'll simplify. So 5 divided by 2 minus 7 over 4. In order to subtract this, I need to get the same denominators. So that would be 10 over 4 minus 7 over 4. So then y will equal 3/4. So my solution to this system would be the ordered pair, 1/2 and 3/4. Awesome. Okay, objective number 3, solve linear systems by addition. So when we use the addition method, we want to have the same coefficient for one of the variables in both equations with opposite signs. We may need to multiply one or both equations by some non-zero number so that the coefficients of one of the variables, x or y, become opposites. Then, when the two equations are added, this variable is eliminated. That's why this method, or the addition method, is sometimes referred to as the elimination method, because you're eliminating one of the variables in order to find the other variable. Okay, so our steps here in order to solve a system of equations by addition or elimination, we first align the equations in the format ax plus by equals c. This allows us to see exactly what's going on with our coefficients in front of our variables. Step 2 will multiply one or both equations by a number to result in a variable with the same coefficients. Step 3, we will add or subtract the equations to eliminate a variable. Step 4 will solve for the variable. And then step 5, we'll use substitution to solve for the other variable. Okay. So let's do an example here, number 5. So I have my system of 2 equations. Okay. Now I want to choose a variable to eliminate, and I'll eliminate it by the addition method. So I need to make one of the variables have its opposites. In other words, in my first equation, I have a 3. So in order to eliminate y, I would need the coefficient in my second equation to be the opposite of 3. So -3. Okay. In order to get -3, I would have to create an equivalent equation by multiplying that whole equation by 3. Now, I could have chose x. The first equation, the x has a coefficient of 2. The second equation, the y has a coefficient of 5. Now, I could make those coefficients the same by multiplying the first equation by 5 and the second equation by 2. However, because I want to take the smallest path to the solution, or the shortest path to my solution, where I don't have to have so many steps, I am going to choose y. Now, if you love the steps and you love algebra, by all means, you can take the x variables and make the coefficients the same. So what we're going to do is we're going to multiply this second equation by 3. So that will give us the system 2x plus 3y equals 10. And then we would have 15x minus 3y equals negative 72. Okay. Not 72, 78. I was like, there's something wrong there, right? 6, 3, 8, negative 6, 6 and 1, 78. Okay. Now we want to add. We want to add both of these together. Ooh, that line is a little crooked. Let's do that one again. Okay. Now, in adding both of these together, I would notice that my y variable disappears. So I have 17x plus 0 equals negative 68. So 17x equals negative 68. Divide both by 17, and I'll get negative 4. Okay. So now that I have x, I can solve for y. Now I can choose any of the original equations to find the value of y. I'm going to choose the second one. So 5x minus y equals negative 26. So 5x, I need to substitute in x. So 5 times negative 4 minus y equals negative 26. So negative 20 minus y equals negative 26. So I'll add 20 on both sides. Then divide both sides by negative 1. Okay. So the solution to this system would be the ordered pair, negative 4, 6. Okay. Alrighty, next. Okay, we're going to solve this system of linear equations. Now, right off the bat, you would have noticed that this system has quite a bit of decimals. Okay, so in order to get this system into a format that I can see a little bit clearer, easier to work with, I'm going to create equivalent equations. So I'm going to multiply my first equation by 10 because the highest decimal value or place value that's present is the tenths place. So to get all whole numbers, I'm going to multiply everything by 10. In the second equation, the highest decimal place value is the hundredths. So I'm going to multiply everything by 100 in order to get the decimals to whole numbers. So I'll have 50x plus 3y equals 14. And then I'll have 20x minus 10y equals 28. And so now that's my new representation of my system. Wouldn't you agree that this is a lot easier to work with? So now I have to determine which variable do I want to eliminate, the x or the y. Either one. I can either make the coefficients for the y opposites, or I can make the coefficients for the x the opposites. And I'm going to do the x this time. Okay? So I'm going to multiply, and let me get a different color here. I'm going to multiply the first equation by 2 and the second equation by -5. That way I get 100, but of course opposite signs so that they can cancel out. So that would give me 100x plus 6y equals 28. Then I'll have negative 100x plus 50y equals negative 140. So now I can add both of these together. The x coordinates, the x terms, cancel out. And then I get 56y equals negative 112. So 56y equals negative 112. Divide by 56, and y equals negative 2. Okay. So now I want to find the x variable. And I'll do that by substituting the y answer or solution that we got into one of the original equations. So I'm going to do the first one, which is 5x plus 0.3y equals 1.4. So I'll have 5x plus 0.3 times negative 2, which equals 1.4. So 5x minus 0.6 equals 1.4. So 5x equals 2. And x equals 2/5. So the solution to my system is the ordered pair 2/5 negative 2. Okay. All right, number 7. Okay, so we have a system here. And in order to use the addition method, we want our equations first to be in the form ax plus by equals c. Now we have quantities here being multiplied by a factor. So let's get this into that format. We'll do that by first distributing our factors, and then we will rearrange the terms so that we're in the format ax plus by equals c. So for the first one, we'll have 3x minus 3 plus 10 equals negative y. So 3x plus 7 equals negative y. So 3x plus y will equal negative 7. For the second one, we'll have 6y minus 30 equals 4x minus 28. So 6y, I did the equal sign. If we move the 4x to the left, we get negative 4x, and then 30 minus 28. So 6y minus 4x equals 2. Okay. So our system now is going to be 3x plus y equals negative 7, and negative 4x plus 6y equals 2. Awesome. Okay, let's choose a variable to eliminate. The first one my eyes go to are y, because all I'll need to do is multiply my first equation by negative 6. Okay, so let's do that. So we'll get negative 18x minus 6y equals negative 42. And we will add it to the second equation, which is negative 4x plus 6y equals 2. Okay. We will then get negative 22x plus 0 equals 44. So negative 22x equals 44. We'll divide both sides by negative 22, and we get x equals 2. Okay. So now we will substitute in x equals negative 2 into one of the original equations, and I'm going to choose the first one. So let's rewrite that down. So when I substitute in -2, I can then simplify. So that's 3 times -3 plus 10 equals -y. So -9 plus 10 equals -y. So 1 equals -y. So y equals -1. So the solution is the ordered pair -2, -1. Whew, that was fun. All right, objective 4. We're going to identify systems that do not have one ordered pair solution. So right in the beginning, we looked at the 3 different types of solutions. You could have one solution, no solution, or infinitely many solutions. So we did just quite a bit of problems that had a system of equation with one solution. So in these 2 problems here, it's going to show us what a system would look like if our solution was infinitely many solutions or if we had no solution. And let's begin with number 9. Okay. All right. Now this system contains fractions. So we looked at a system with decimals and I showed you how to convert that to where your coefficients are whole numbers. Now for this system, we have fractions. So in order to make this look more easier for us to solve, we're going to convert our coefficients to whole numbers as well by getting rid of denominators. So the first thing that we're going to do is we're going to multiply each equation by its LCD. So in the first one, the denominators are all 3. So we'll multiply everything by 3. And in the second one, the denominators are 2. So we'll multiply everything by 2. So our system now looks like 3x plus 5y equals 1. 3x plus 5y equals 4. Okay. So we need to now choose a variable to eliminate. We can do the x or the y. So let's do x. So we'll multiply this by -1. So we would have 3x plus 5y equals 1. And then we'd have -3x, -5y equals -4. So that comes out to 0 plus 0 equals -3, and 0 does not equal -3. So there is no solution. There is no solution to this system. Okay? This is what you would call an inconsistent system. Okay? So when you are solving and you get down to the point where you have 2 values that are not equal to each other, you would have no solution. All right, let's do number 10. Oh, our second equation here is already written in terms of x, meaning we know what y equals. So we can just use the substitution method to find our value for x. So we'll take our first equation and then we'll substitute in y. And now we'll solve for x. So we'll distribute the -5. Then we will combine like terms. And we get 30 equals 30, which is true. Okay, so in this case, there are infinitely many solutions. Okay, And this would be called a dependent system. Okay. Where our first coordinate is x and our y coordinate is 2x minus 6. And we got that right here with our second equation. So when we substitute in an x, we get a y. Awesome. All right. To close out this section, let's solve some word problems, application that involve system of linear equations. Okay. So our first one here says a company that manufactures running shoes has a fixed cost of $300,000. Additionally, it costs $30 to produce each pair of shoes. They are sold at $80 per pair. Okay. Before we go into our questions, let's first make sure we understand what they just told us. So the company is manufacturing shoes, and the fixed cost of doing that is $300,000. Okay. Now, in addition to that, it costs them $30 to produce each pair, and they are sold at a rate of $80 per pair. Okay. So A is telling us to write the cost function C of producing X pairs of running shoes. Now, the cost function, all right, the cost function is going to be the sum of the fixed cost and the variable cost. So C of X is going to equal the fixed cost, which is the 300,000, plus the variable cost. And that's going to be 30x, because x is the number of pairs of running shoes. Okay. Now B asks us to write the revenue function R from the sale of x pairs of running shoes. So the revenue is going to be the money generated from the sales of the running shoes. So that would be R of x equals 80x. Okay. Now C is asking us to determine the break-even point and describe what it means. So the break-even point occurs when your cost function and your revenue cost function intersect. In other words, when they equal. So when C of x equals R of x. Okay. Well, we know C of x equals 300,000 plus 30x. And we know R of x equals 80x. So we can set them both equal to each other and solve for x. Okay, so we'll subtract 30x on both sides, divide both sides by 50, and we get x equals 6,000. Okay, so we have the x, now we need y. Well, we're going to take x and substitute it into either equation. So let's substitute it into the revenue equation. So that's 80 times 6,000, which equals 480,000. So the break-even point is 6,000 and 480,000. Okay. This means the company will break even if it produces and sells 6,000 pairs of shoes at a total cost of $480,000. Oh boy, let's redo that. There we go. Sometimes my pen doesn't draw straight. There we go. Alrighty. Cool. Next one. David borrowed a total of $10,000 to pay for his final year of graduate school. He borrowed part of the money through his school with a Perkins loan that charged 5% simple interest per year, and the remainder of the money from his aunt at a rate of 1.4% simple interest per year. At the end of the year, he paid $428 in interest. How much did he borrow from each source? Okay, let's get a different color. Let's go green. So we know that David borrowed a total of $10,000. Okay, he had two loans. He had a Perkins loan and he had a loan from his aunt. Okay, now the Perkins loan charged 5% simple interest, and his aunt's loan charged 1.4% simple interest. The total interest he paid was $428. We want to know how much did he borrow from each source. So let's first let X equal the amount of the Perkins loan, because we don't know that. That's what we're trying to find. And then we're going to let Y be the amount of his aunt's loan. Now, the interest formula is given by I equals PRT. Okay? And we know time is 1 year. Okay? So we need to now set up our system. First things, we know that he borrowed a total of $10,000. So between the Perkins loan and his aunt's loan, they equal $10,000. So that means X plus Y is going to equal $10,000. Okay. Now we know total interest that he paid was $428. So the interest from the Perkins loan plus the interest from his aunt's loan equaled $428. Now the interest of the Perkins loan is going to be PRT, where P is principal, R is the rate, and T is time. Now we know time is 1, so we're just really focusing on P and R. Principal is how much or the amount that you started with. We don't know the amount of the Perkins and we don't know the original amount of the aunts, but we gave them both variables. So to find the interest of the Perkins, we're going to take X times its interest, R, or its rate, R, which is 5%. So that will be 0.05X. For his aunt, it's 1.4%. So that would be 0.014Y. And it equals 428. Okay? So that is our system. Now we need to determine what method we want to use to find the amounts for the Perkins and for his aunt's loan. I would recommend using substitution. And I would use substitution because I can rewrite this first equation where X equals 10,000 minus Y. I can then take that expression for X and substitute it into my second equation. So 0.05 times 10,000 minus Y plus 0.014Y equals 428. I'll distribute the 0.05 and I would get 500 minus 0.5y, and then bring down all the other parts of my equation. I then will combine like terms. So 500 minus 0.036. Y equals 428. I will subtract 500 on both sides, and then divide by negative 0.036. That will give me 2,000. Okay, so now I know what y equals. I can figure out x. So I want to go back to one of my original equations. So I'm going to take x plus y equals 10,000. I'm going to substitute in y. Then subtract 2,000 from both sides, and I get 8,000. Okay, so that means David borrowed $8,000 from the Perkins loan, because X represents the amount of the Perkins loan, and $2,000 from his aunt. Alrighty, great. Okay, number 13. We are now going to solve this system, or solve this problem using a system of equations. Okay, so a plane flies from Atlanta to Los Angeles against the wind in 5 hours. The return trip with the wind takes only 4 hours. If the distance between Atlanta and LA is 3,200 kilometers, find the speed of the plane in still air and the speed of the wind. Okay, so it's asking us to find the speed of the plane in still air and the speed of the wind. So we don't know those, so let's give them variables. So we'll let x equal the speed of the plane in still air, and we'll let y equal the speed of the wind. Okay. Something to note, that distance equals your rate or speed times time. So let's set up our problem here. And I'm going to draw us a box to help us visualize this. And I need 4 columns. There we go. And this is D, R, T. And this will be with, wind, against, wind. And I know that because my problem tells me. So in the first problem, it says a plane flies from Atlanta to Los Angeles against the wind in 5 hours. So the time it takes for the plane to go against the wind is 5 hours. So this is T. This is the time. The return trip with the wind takes only 4 hours. Okay. If the distance between Atlanta and LA is 3,200 kilometers, so whether you're going with the wind or against the wind, the distance doesn't change. Okay. What is the rate or speed? Remember, this is distance. This is the rate or speed. Okay. Now, if you're going with the wind, right? Thinking about this, if I'm in a plane and I'm going with the wind, or even if you're like running and you're running with the wind, you may tend to go faster. So the speed of the plane plus the speed of the wind is going to increase. Now, if I'm going against the wind, I'm going to have some resistance. So I'm not going to be able to go as fast. So that's going to be x minus y. Okay, because the speed of the plane will be going faster than the speed of wind. Okay, so we now have our equations, setting it up in terms of d equals rt. Okay. So we'll have 4 times x plus y, that's the time times our speed, equals 3,200. Then we'll have 5 times x minus y equals 3,200. Okay. And now we need to solve our system. Okay, so let's do that. All right, I got a fresh sheet of paper. I'm just going to rewrite our system. And 5. All right, we did a similar problem like this in this section. So let's distribute our factors so that we have everything laid out. So that would be 4x plus 4y, then 5x minus 5y. Okay. Now we want to determine what variable to eliminate. Let's eliminate the x. So what I'm going to do is I'm going to actually divide everything in the first term by 4 and then divide everything in the second equation by 5. So that would give me x plus y equals 800. Second equation, x minus y equals 640. Adding that, I'll get 2x plus 0 equals 1,440. So 2x equals 1,440. So x equals 720. Now I can substitute x back into one of the original problems. And I'll do the first one. So I'll have 4 times 720 plus y equals 3,200. I can divide both by 4. So that's 720 plus y equals 800. Subtract 720. So y equals 80. Okay. So that means the speed of the plane was 720 kilometers per hour, and the speed of the wind was 80 kilometers per hour. Okay, that's wonderful. So I wonder, all those times I take flights, or you might think of this too, and they say your flight's going to be 2 hours and 30 minutes, and you get there within an hour and a half. And you're like, why did we get here so fast? It could be because of the wind. You never know. All right. Well, that concludes section 5.1.